ASTRA from the Space Hardware Club at the University of Alabama in Huntsville is proud to present our 2025 System Acceptance Review. Our team of over 50 members have been working tirelessly throughout the year to redesign our core rover and science modules, as well as make critical enhancements to our robotic arm and communication systems.
This year, the core rover submodule has been fully rebuilt to enable all mission-specific rover configurations. It consists of a carbon fiber and foam composite sandwich chassis, a geared differential averaging system, and redesigned software and electrical systems.
Taking advantage of the internal volume provided by the composite chassis, the core electronics have been completely redesigned to maximize accessibility and improve cable management. The main computer, an Intel NUC 13, communicates with each module, including core, biosensor, arm, drill, and end effector, using a newly implemented CAN protocol. ESP32 microcontrollers manage low-level logic throughout the rover, while PCBs handle power distribution and communication within each module.
The modules for each rover configuration communicate peer-to-peer through ROS2, allowing for independent control and feedback between modules. This design ensures flexible and efficient communication to each separate module via the base station. The base station can run locally on any device, allowing for versatile operation and eliminating single points of failure.
Communication with the rover has been handled through two radios communicating via 2.4 and 5 GHz. New antennae have been selected to optimize the range and improve the signal strength.
The autonomous navigation subsystem has seen substantial refinement in its capabilities since last year. The rover's new autonomy architecture utilizes OpenCV alongside the Yellow V8 neural network trained on a custom dataset. This allows for the rover to detect all relevant competition objects such as a mallet, bottle, and Aruco tags. The rover utilizes GNSS satellites to determine its positioning and then uses that information alongside its IMU bearing to precisely navigate to specified points. From those given coordinates, the rover then autonomously searches the surrounding area for competition objects using a horizontal sweep search pattern. The system obtains depth data used for object avoidance and local pathfinding from a front-mounted depth camera.
The ARM has been redesigned for the 2025 equipment servicing mission, maintaining 6 degrees of freedom and a 1.25 meter reach. A new bearing stack rotary turret has been implemented to increase stability, and the cycloidal gearboxes have seen revisions that decrease backlash and increase controllability for dexterous tasks. The end effector has been upgraded with a lighter motor, utilizing a new Acme drive screw and linear bearings to increase mechanical efficiency and maintain strength. Cycloidal joints are powered by Neo 550 motors with SparkMax controllers, while absolute position encoders provide high-resolution feedback. The software has also been revised to implement onboard forward and inverse kinematic solvers for user-friendly manipulation. Once implemented, inverse kinematics will enable autonomous operation for the keyboard task.
This year, a custom reconnaissance drone has been developed to scout safe terrain and read on-field signs during the extreme delivery mission. High-efficiency motors, LiPo batteries, a Foxy or Razor Mini FPV camera, and a strong carbon fiber frame enable long-range flight and observation.
The rover is capable of operating at a distance of 1 kilometer while using its suite of cameras to allow operators to interact with the environment accurately and precisely. These include a live view directly on the end effector, as well as around core module to provide front, rear, and top-down views from the antenna mast. The arm is capable of manipulating masses in excess of 5 kilograms to complete mission objectives. To facilitate traversal over difficult terrain, the drivetrain uses 100-to-1 gear-reduced Neo 550 brushless motors with SparkMax motor controllers for improved torque output and speed control, enabling precise command over the rover's mobility. Large diameter compliant TPU wheels enable the rover to navigate deep sand, gravel, and large rock fields, reducing the risk of entrapment. The chassis includes an easily accessible emergency stop button in the event the rover endangers itself or others.
The science mission configuration for this cycle has been designed to achieve two primary missions: surface sample collection and chemical analysis, as well as subsurface sample retrieval and environmental condition surveying at depth. For surface sample collection, a small telescoping robotic arm is used with 3 isolated cyclonic separator systems to collect topsoil and divide it between 3 test tubes per site for analysis at up to 3 potential locations.
3 chemical tests will be conducted on the surface samples. The first will directly determine the presence of life, a bicyclinic acid assay for detecting proteins, while the acetic acid test detects carbonates, a potential sign of extinct life. The last test assesses the suitability of the site for supporting life by using methylene blue to determine the presence of perchlorates, a compound detrimental to extant life.
Once a viable site has been selected, the subsurface sample is collected with a drill end effector mounted to the arm. The drill can be sealed in situ once the proper depth of 10 centimeters is reached, isolating the subsurface sample. A sensor is located inside the drill to collect temperature and humidity conditions at depth.
This concludes our System Acceptance Review. Thank you for your consideration. We look forward to seeing you in Utah this summer.